The final that we take is an ACS like standardized exam, right?
Yeah, don't worry about that.
I'm worried about
Don't worry about it. But if you want to get a study guide, Dr. Paiva has some for sale. Okay. I can't tell you how much. It's 25 or under. Let's go with that.
I think they went, yeah, I think they're 25 because we had to like, at least for the Gen Chem ones, we had to start charging like $5 more.
Yeah, because they raise the prices on it probably at ACS. So, I mean, I don't think they try to make money off you. Okay, honest. It's just an assistance thing. Because if you go order it yourself, you're going to have to pay shipping. It's going to cost you more. Are you scared now? All right, so I'm going to do this. Started.
Yeah, I got my grade. I was like,
Okay, so what have we been talking about? I know you slept since then. What did we do? What were we doing on Monday? What were we doing?
Nucleophiles.
Mm-hmm. We're doing the SN2 mechanism. Okay, what's S? Substitution. What's N? Nucleophilic. Yes, or nucleophile. I'll take that. What's a 2?
Steps.
2 molecules present in the rate determining step. That's real important that you get that little thing there. It'll keep you from getting it mixed up later. Okay, so we're going to talk a little bit more about nucleophiles. Stronger bases are better nucleophiles. Okay, so if you look down here, we have OH minus and we have water. Both of them can function as nucleophiles because they both have lone pairs on the O. But the one that has the negative charge will be the better nucleophile. Same thing with methoxide ion. You've got a negative, and then you've got the CH3OH, good old methanol. The methanol can function as a nucleophile, but the methoxide ion is a better nucleophile because it is negatively charged. Does that make sense? Do you feel okay about that? Okay, down here we have NH2 minus, and then we have another N minus compound. Okay. Okay, I'm going to show you this video. Oh, yeah, be that way. Is it going? It's going, yes. I had to upload them to YouTube. That's the only way I could get them to work in this program.
4 test tubes contain a solution of sodium iodide in acetone. The following isomeric alkyl halides are added to separate tubes: 1-bromobutane, 1-bromo-2-methylpropane, 2-bromobutane, and 2-bromo-2-methylpropane. The solution containing the primary halide, 1-bromobutane, quickly becomes cloudy as sodium bromide precipitates.
You see that?
The more hindered primary halide, 1-bromo-2-methylpropane, reacts after about 5 minutes. The secondary halide, 2-bromobutane, reacts after about 13 minutes.
Okay. Okay, so we took RBr, some alkyl bromide, and we added NaI, Okay, and we substituted what for what? What was the reaction? What did we substitute? I and the Br. They swap positions, okay? And we ran the reaction in acetone. When you do that, sodium bromide is not soluble in acetone, but sodium iodide is. So you can tell the reaction is completed because the sodium bromide precipitates out, okay? That's what they're timing, okay, on the video. Okay, so which one worked the best? Which was the fastest? Maybe that would be a better way of saying it. Do I get the first one, which was 1, 2, 3, 4. This one. This is what kind of alkyl halide? Classify it. Primary. Okay, that was the fastest. Okay. This one was the second fastest. Now, if you classify that one, what do you get? How do you classify an alkyl halide? Look at the carbon the alkyl halide is attached to. Is it primary, secondary, or tertiary? This is secondary? Primary, right? How many carbons is this carbon attached to? 1. It doesn't matter what this one is over here. Okay, only that one counts. Okay, it's primary. This one is still primary, but the second one was slower than the first one. Okay, even though they were both primary. Okay, what was our third slowest? What kind of alkyl halide was this one? And the one that never reacted at all, even though they let it sit there for a long, long time, was this one. And what kind of alkyl halide is this? Tertiary. Do we see a pattern? Okay. Yeah. Okay. So why? Here is the same kind of thing. We have methyl, and that one reacts 1,200 times faster than the secondary one. Okay, so do you understand what relative rate means? Okay, it's relative to this one. This one was, no matter what the number is, it was given a rate of 1. And this one is 16 times faster than this one. This one's 40 times faster than that one, and that's 1,200 times faster than that one. Now, why all of a sudden is that methyl one? That wasn't in the other thing. Why is that one faster? Is that primary, secondary, or tertiary?
A methyl, it has to be primary.
The methyl is just the methyl. How many carbons are directly attached to that carbon?
None.
None. Okay, so what that carbon has on it are 3 hydrogens. This compound now has 2 hydrogens and a methyl. This has 2 hydrogens and an ethyl. And what did we have? I want to write over here. What did we have on that weird one? We had an isopropyl and 2 hydrogens. So what's happening is as these groups are getting bigger, the reaction is getting slower, okay? That tells us something about the mechanism. And look at this one. They didn't get a number, okay? Here is how hydroxide ion would attack different alkyl halides. So here is, remember that the nucleophile is going to come in from the back and the group leaves from the front. Right. What is that little term for that we said? Backside attack. All right. So here is, let me get out of red because that ain't going to work. I don't even know if black would be good. All right. So here's my nucleophile. It's going to go here and this is going to leave. This is the methyl one. Okay. Let's look at this one. Here, my nucleophile is going to come in here, and this one's going to leave. This is the CH2CH3 one. Okay. All right, here, this is the isopropyl one. This is coming in and this is leaving. So as this has to get in here, notice what is happening. We are changing what is attached to the carbon that the reaction is occurring to. This one has 3 little hydrogens. This one has a little couple hydrogens, and that's got a methyl. Okay, this one got 2 methyls. And what does this one have? 3 methyls. Remember, this one was too slow to measure. Okay, so those big methyls are blocking the carbon where the reaction is going to occur. This carbon right in, oops, yeah, that was it, here. Okay, the methyls are blocking that carbon. So the nucleophile can't get in there. Okay, or it can get in there, but it's more difficult. Okay, that's called steric hindrance. I don't know what's under these boxes. We'll find out in a minute. Okay, that's called steric hindrance. Okay, because they're blocking the site where the reaction is going to occur. So what will affect how fast an SN2 reaction occurs is whether the carbon that the halogen is attached to, if it has large bulky groups on it, okay? Also, the nucleophile that's coming in, if it's big and bulky, that will also slow down the reaction because it won't be able to get in. Now, in all these examples, the hydroxide ion is fairly smallish. But if you start changing this H to different R groups, it's going to get bigger. It's going to have a harder time getting in there. Okay? All right, let's see what's under these boxes. Okay. Oh, looky there. Bulky groups inhibit reactivity. It's called steric hindrance. Okay? No SN2 reactions on tertiary centers. Did you notice I didn't draw the little arrows on this one like I did on the other 3? I did that on purpose. Because there's no SN2 on tertiary centers. Okay, and is there something down here in there? Okay, so here's the reactivity of just the alkyl halides. Okay, methyl, then primary, then secondary, then tertiary. Tertiary is least reactive. Methyl is most reactive. So we're going from most to least. You probably need to write that down. I bet I would have not put that on there. I probably didn't put this in there either because I wanted you to write it in. Every time you write it, it helps you remember. That's my logic anyway. Okay. Now, remember that other one. This one. Okay, so why, I'll make sure I make it skinnier. Why is this one slower than this one? They're both primary. What do you think? Because this is going to be blocking that site. Okay, and so even though it's one away, it's still going to block it. And so it slows it down. It's not that it doesn't react. It just slowed it down. Okay? Okie dokie. All right. Identify the strongest nucleophile. Which nucleophile up there do you think is the strongest? I don't remember him telling me he wasn't going to be here. Okay. All right, there's 23. How'd you do? Wow, we got every answer. Okay, so first of all, what did we talk about on the very first slide? What makes a nucleophile better? A stronger nucleophile. If it has a what? Negative charge. Okay, so that cuts out this one and this one because these two are negative. Do you see that this is the negative of that one and this is the negative of that one? Okay. Not that I could point very well, but you know. All right, so what's different between those two? They're both O minus, so that isn't a factor yet. So what's different about them? This one is a methyl, and what's this one? Tert-butyl. Okay, which one do you think is bigger? More bigger. The tert-butyl's bigger. So when it wants to get into that carbon that has the leaving group on it, it's going to have a harder time because it is bigger. Okay, now that doesn't mean that none of these are nucleophiles. They're all nucleophiles because they all have lone pairs. Okay, so they can all function as nucleophiles. These are just stronger ones because they have that negative charge. I tried to draw in the lone pairs. Sigh. Okay, when you do an SN2 reaction, your nucleophile comes in from the opposite side where the leaving group is. So look at this reaction down here. This is R2-bromobutane, and your hydroxide ion is your nucleophile. Okay, it always comes in from the back, and the halide leaves from the front. Okay, so notice what happened to our stereochemistry. It gets flipped. Okay, it gets flipped. When stereochemistry gets flipped, it's called inversion of configuration. Okay, so this one is R, and the one that we made is S. Okay, even though you don't know how to do alcohol nomenclature yet, it doesn't matter. Okay, this reaction is considered to be stereospecific. One stereoisomer gives a specific stereoisomeric product. What if I did this reaction and I started with S2-bromobutane? What do you think I would get? R. You got it. Okay, you get the inversion. Okay. Okie dokie. Now, you have to be a little bit careful because R and S are based on those priority rules. Remember those? Okay. When you're basing it on priority rules, depending on what your structure is and the nucleophile coming in, the priorities could flip-flop, and you could start with R and get R. Okay? So you have to be careful. It's how it looks is inverted. Okay? How it looks is inverted. Do you see that here the BR was on the right and the H going back? The H is still going back, but the OH is over on the left side. Okay? It's inverted by how it looks. Okay, does that make sense? Why you have to be careful. Don't just go, R must give S. Look at it and make sure R gave S. Okay, that it's the inversion. Okie dokie. Okay, so now we're going to look at leaving groups. Leaving groups are the things that leave. Adios. Okay, so in this example, we have the exact same alkyl halides, or alkyl groups. All we changed was the halide. That's what I want to say. Okay, and so OH minus, what is this functioning as? What is OH minus? That's your nuke. Okay, the yellow ones are all your leaving groups. Okay, now over there is relative rate. So who got the one? Fluoride. Okay, And when you use chlorine, it's 200 times faster. When you use bromide, it's 10,000 times faster than using fluoride. When you use iodide, it's 30,000 times faster than when you use fluoride. So what does that tell you? That tells you who is the best leaving group. Who's the best leaving group? Iodide. Okay. Who is the worst leaving group? Fluoride. Do you notice it goes in order down the periodic table? Okay. So not only is the electronegativity getting less, but the size is getting less. Okay. Turns out that iodide is the weakest base. Okay. Weaker bases are better leaving groups. Okay. Weaker bases are better leaving groups. And this is true in like 5,000 other reactions that we're going to do. It's about that many. All right. It'll at least feel like that many. Okay. What did you need? Oh, thank you. I didn't even know. Now, in this case, all the R's are the same. All that's changing is the alkyl halides. If you want to start changing R's and alkyl halides, then it's a big mess. It's a hot mess. So pretty much we're always just going to change one factor. Okay. If you wanted to do, you could do a study and you could do that. Okay. And monitor the reaction and see, well, which factor is greater? The fact that I changed it from bromine to iodine, or the fact that I went from isopropyl to ethyl? Someone's probably done it.
So we can't tell that just by like.
No, which factor is, yeah. And it probably is dependent on your nucleophile and your solvent. Okay. All right. You got that? We're good? Yeah, we're good catching that. All right. So the best leaving groups are going to be electron withdrawing to help polarize that carbon leaving group bond. They're going to be stable and they're going to be weak bases. Okay. And then there's this little term, polarizable. What does that mean? Polarizable means that things are squishy. The electron cloud is squishy and it can skew this way or skew that way. And that helps stabilize the negative charge that you get when you leave. It also helps to stabilize the transition state, because in the transition state, remember, you're halfway in between. So you're making a bond and breaking a bond so that you can fall down the other side of the ski slope. Okay, so here are your ions, weak bases that are common leaving groups: chloride, bromide, and iodide. Do you notice that fluoride is not on the list? Fluoride is a sad leaving group. It don't leave very much. We don't use them. That's okay, they're hard to make anyways. Okay, here's a good leaving group: these sulfonates and sulfates and phosphates. This happens, especially the phosphates, in your body. Okay, why are those such good leaving groups? Do you have any idea? Yeah, and what can you do with those double bonds? What? Resonance. So do you see that every one of these is going to have resonance for it? That's going to super stabilize those leaving groups. Okay. Okay, now the other thing that are really good leaving groups are neutral molecules, in particular small neutral molecules. So you will see water used as a leaving group, little alcohols, little amines, okay, used as leaving groups. We're really not going to do sulfides and phosphines. We'll talk about phosphines next semester in one reaction. Okay, but this is the biggie. Okay, and let me ask you this. What is the conjugate base of water? What? Hydroxide, OH minus. What is the conjugate base of an alcohol? No, RO minus. Okay, to figure out the conjugate base, you have to remove a proton. Okay, this is not the conjugate base of that. Okay, so before where we showed methoxide ion as being a good nucleophile. It's a good nucleophile, but it's a crummy leaving group. If you want to make it leave, you put a hydrogen on it first. Okay, and we're going to do that eventually. I don't know if it's today, but. Okay, so what's the deal with iodine? Okay, so if you manage to look up what iodine's electronegativity value is, okay, it's not greater than carbon's. It's less than carbon. Okay, it's less than carbon. In fact, the Ci bond is polarized the other way if you just look at electronegativity. Okay, so why does this even work? Okay, it works because the iodine is big. I mean, it's got how many electrons around it to begin with? 53. Okay, chlorine only has 17. All right, we have 53, and when we leave, we're going to have 2 more. Okay, so we have a huge electron cloud. It's like the big marshmallow and the little bitty marshmallows. Okay, the big marshmallow is squishy. What happens to the little ones? They get stale, right? And they get hard. Okay, they don't last as well. Just put them in good Tupperware. Okay, but the big ones are squishy. In fact, you usually finish that bag, right? Okay, because polarizability, that electron cloud on the iodide, even though it's only one atom, is going to be able to distort itself and keep that negative charge stabilized. Okay, that's how come. Okay, it is amazing at it. It is so good at it that alkyl iodides are very, very reactive. And they're like the choice. If you want to make something and you have to do an SN2 reaction in the making of it, you try to get it so you can get an iodine on there. Okay, because it works so well. Okay, hint, do not write SN2 reactions that show hydroxide ions, OH minus, alkoxide ions, RO minus, or other strong bases as leaving group. Another example would be NH2 minus. Okay, that'll be another one. Those are not going to be good leaving groups. Okay, your halides, chloride, bromide, and iodide, are going to be good leaving groups. Okay, now do you feel that you know if it's a strong base or not? How are you doing on that? I mean, if I write down ethanol, you think, is it 5 o'clock? You think, is that a strong base or a weak base? In the grand scheme of bases. What do you think? Weak. It's weak. How do you know it's weak? Number one, it doesn't have a negative charge. Okay, that's number one. If I write NH3, is that a strong base or a weak base? Weak. It's probably the one that you learned in general chem as a Bronson-Lowry base. That isn't the other kind, right? That isn't the Arrhenius definition. Okay? Remember that these things, the CO bond in these is covalent. You do not take ethanol, dissolve it in water, and get hydroxide ions. You just get ethanols dissolved in water. Okay? That's why you can drink it. If you're over 21, you do so in moderation. Don't drink and drive. Okay? Okay? This does not give up OH minus. Okay? So this would be a good leaving group. Okay? It'll help when you see it, but Okay, to kind of get you a little bit. All right, we'll keep working on that. Okay, crown ethers are compounds that solvate the cations and make the anions more nucleophilic. Okay, so we talked about how fluoride was not a very good nucleophile. Okay, it's not a very good leaving group. Okay, well, somebody wanted it to be a nucleophile, and they came up with a trick. This is the trick. They use this thing called a crown ether. Okay, a crown ether has all these oxygens, okay, in a ring with carbon atoms, and it's kind of repeating. And this one is called 18 crown 6. So the way you get that is there's 18 atoms in the whole thing, right? Yeah, 3, yeah. And there are how many oxygens? 6. They're always arranged evenly. Okay. What if you could have a bigger one? Okay, where you had 7 oxygens in it. Your hole in the middle is going to be bigger. Okay, so what they've done is they've designed these compounds so that they will fit specific cations on the periodic table. So if you wanted to solvate lithium ion, you would use a smaller one. Okay, which one do you use? Don't worry about which one. I don't know all of them. Okay, but by using this, okay, when you have KF, you have a potassium ion and a fluoride ion, and they're bound together, right? Okay, well, what happens if you take this out of the picture? That's what we're doing. We're taking and caging it like inside that ether. So now your fluoride ion is just hanging out. What do you think it does to the reactivity of the fluoride ion? It makes it more reactive because the positive, its positive ion buddy is no longer there. So now all of a sudden this is really good. Okay, now I want you to draw the mechanisms. So the fluoride ion is going to go where? Where? Which carbon?
Carbon attached to
Okay. And it might take that circuitous route. You never know. And then what happens to the electrons in the CCl bond? They go to the chlorine. So you get this and the chloride ion. Okay. And if that was a chiral center, it would have been inverted, right? Flipped. But that's not chiral. Why not chiral? Because it has a plane of symmetry. And it does not have 4 different groups attached to that carbon. Okay? It has 2 hydrogens. Okay? All right, that's it for crown ethers.
Yeah.
Just to show you what they're used for. What? No, just that the crown ether solvates the cation and makes the anion more reactive. That's it. So if you see that on the thing, that's what it's doing. Oh, I didn't tell you what this was because I don't think we've seen this yet. This is acetonitrile. It's a nice polar solvent. Okay? It's CH3 bonded to a C. And how is that C bonded to the N? Yes. Okay, that's all. I just want to make sure you knew what that was because that'll show up again. I feel like I'm tripping on this thing. It's driving me nuts. Okay, so solvents are going to be a factor in this whole thing too. Okay, so you can have polar solvents or you can have nonpolar solvents. How do you know if they're polar? If I write a solvent up here, can you tell me if it's polar or not? You think? How are you going to decide? What do you look for? Yeah, you look for polar bonds. Okay, so if I write this, chloroform, commonly used solvent. You may have used it. I don't know. Is that polar or not? Is there polar bonds in it? Okay, there's one other factor you have to look at, and what is that? Shape. Right? Because okay, so HCl, Cl, Cl. Some of them are going to be canceling each other out, right? Okay, remember, if you pull evenly, you're canceling out. So you have to take into consideration polar bonds and the shape of the molecule. Okay, so what if I have this compound? No what?
It's not polar.
It's not polar. Okay, what is that called if it's not polar? Non-polar. Just making sure. Okay. Okay, so that's polar or non-polar, and that's something we've already talked about some. Okay, what about this protic or aprotic? Okay, protic means it has a hydrogen available for hydrogen bonding. So what are some hydrogens that are available for hydrogen bonding? Do you remember? What's hydrogen bonding? Okay, a hydrogen bonded to an O, an N, or an F can do hydrogen bonding. Hydrogen bonding is between molecules. Okay, you all know this compound. What is that?
Water.
Water, okay. Water has a weight of, what's its molecular weight?
18.
18, just round it. Okay, what is its boiling point? I have to, it's so high I had to write it twice. Okay, 100 degrees C. Why is it so high? It only weighs 18. It shouldn't be so high. Why is it high? Because of the hydrogen bonding that has to be broken. Okay, so protic solvents have that hydrogen available for hydrogen bonding. An example of a polar protic solvent is water. Okay, a lot of organic compounds are not soluble in water though. What's another polar protic solvent? Can you give me another example? What about this? Methanol. That's a polar protic solvent. Okay, all your alcohols are going to be polar protic solvent. Okay, any amines that have hydrogens on the ends are going to be polar protic solvent. Okay, so what do you think aprotic is?
Hydrogen bonding.
It means there is no hydrogen available for hydrogen bonding. I'll move. Okay, so how can we be polar and not have a hydrogen available for hydrogen bonding? Well, we have to not have an H attached to an O or an N. Or an F, but if you're this, what are you? You're a compound. That's it. There isn't going to be an F with an H on it in an organic molecule or in it. That's it. That's only one. So all you have to worry about are O and N, even though I know that we tell you that a billion times. Okay, so what about this compound? Anybody know what that is? No? Am I going to have to go talk to Jay-Z? Is that what you're telling me? It's what? It's acetone. Did we not use it to do our dishes a billion times? Always know what you're touching. Y'all wear gloves, right? When you do your dishes. Okay, acetone. So why is it polar? It's polar and it's aprotic. So why is it polar?
Oxygen.
Because you have that C double bond O. Where's the negative side of the molecule? It's where the what? Where the O is. Okay. All right, here's another one. The one that was on that other slide. Acetonitrilo. Man. Okay, where's the negative end? Where the nitrogen is. Okay. Here's another one that's real popular. DMF. Dimethylformamide. Okay, so hang on, I'm going to draw it because it has an amide in it. Okay, how is that polar? Where do you think the polarity lies? On which atom? On the O. That's DMF. Dimethylformamide. Do you want me to write that?
Yeah.
Okay.
Actually, I thought you said dimethyl chloride. And I was like, there's not that.
Oh, sorry. I just feel like I'm running out of space. All right. I'm going to go to a different color for the last one that I want to show you, so make sure you can read it. Okay. It's DMSO. And the thing is about these letters, you may see those written on an arrow. Okay. All right, as the solvent. Okay, DMSO is dimethyl sulfoxide. Has anybody heard of it? There it is. All right, do you need me to write that one too? Dimethyl sulfoxide, and it's one word. Put a hyphen. Okay, anybody heard of that? Where?
In research.
In research. Oh, that could be.
Yep.
I don't know. That was what I was thinking. I've had people hear of it because of animals, veterinary medicine. Okay. DMSO is used a lot on horses. Okay, to help their sore muscles or whatever. Okay. It also goes through your skin really readily, and so sometimes they put drugs in them, and then they'll put them on the animal, and it'll go through the animal and get right to where they want it to get, like if someone pulled their muscle. Okay. Now, they used to do that in humans, but they quit doing it. It's not good for you. Okay. So do not put dimethyl sulfoxide on you. Okay. Number 2. If you open a bottle of dimethyl sulfoxide, you have to be careful. It has a distinctive odor. And it's not necessarily really bad, but you'll taste it in your mouth. It's the weirdest thing. Every time I open a bottle of it, I taste it in my mouth. It's the weirdest thing. And I wear gloves and the whole shebang, and I still taste it. It's terrible. You know, it doesn't taste good. And it's weird because I think it's through the vapor. It's going through your skin, and it's weird. Just trust me on that. And it's really thick. Have you worked with it? Did you taste it?
No.
Good. Because it tastes bad. Okay. So what is the big deal about being a polar aprotic solvent? I mean, after all, I gave you 4 of them, didn't I? Okay. They solvate the cations, but not the anions. Okay, so if you have NaBr, okay, and you dissolve it in DMSO, okay, remember what that was. I'm going to just draw it like this. That's why I picked it, because I could draw it like that. Where's the negative part of the molecule? It's on the oxygen. This is the negative part. Am I running out of time? Okay. That's the negative part. That negative part is going to go around what piece of sodium bromide? The cation, the Na+. But where is the positive part of the molecule? It's polar, It's buried. It's covered up by those metal groups. It's covered up by the metal groups. Okay, so it doesn't stabilize the bromide. That makes the bromide more reactive. There's a word for that. It's called a naked nucleophile. What isn't it wearing? It's not wearing solvent molecules. If you put this in ethanol, the H will solvate the halide ion, and the O minus part of the alcohol will solvate the cation. So they'll both have solvent on them. But if you're naked, you want to get dressed. So you run to the molecule, okay, to stabilize your stuff. All right. We're going to start in the middle. Yeah, Glenna. Where's she? There she is. Okay, Tiffany. Morgan. Madison. Tyler. Cassidy. Laisha. Laisha, I know she's here.
Sorry. Hey, I have your
Jessica. Yes. Alexis.
okay, fake.
Which one?
Coming. Caitlin. Katie.
Okay.
Edie. Alexis. Abby.
Abby's not here.
Lindsay.
Oh, sorry.
Brianna.
Yeah, I should everybody got
Jeremy. We already talked about her. Lakeland.
Oh, yeah. Sorry.
Brandon.
Wow.
Skylar.
Yes.
Sorry.
Taylor.
Thank you very much.
Savannah. Andrea. Renisha. Kaylee. Sorry. You need, what you need? Keys. Lab keys. Oh, okay. I guess you can use mine.
No, like I'm not in the lab anymore. You need my lab keys.
Oh, you have to give them to Jay-Z.
Jane, okay.
All right, cool. Yeah. He's taking care of all that.
I do need your signature.
You do?
Yes.
Okay. This is good. Have we been doing it every time?
I missed 1 week. But
Okay, but other than that, we've been doing it?
Yeah.
Oh, I feel like I've only signed like 2 of them.
it's every 2 weeks.
Okay. All right, let's go to the office. And then I can give you a copy of the text.
Abby said that sorry she missed class, but she was having a mental breakdown, so forgive. Yeah.
Hey, question. Have a great day.
Oh, no, did I screw that up?